Hey guys, so we're going to do some more Lewis dot structures. This time we're going to do ions and we're going to do structures that do not follow the octet rule. Okay, so the first one I want to do, I want to draw the Lewis dot structure of hydroxide. Hydroxide, of course, you need to know your polyatomic ions. If you haven't looked at those in a while, you probably want to review them. But hydroxide is OH with a -1 charge. So to draw the structure, I have my O and my H. I know that oxygen normally will have 6 dots around it. Hydrogen will have 1 dot. If hydrogen has 1 dot, it wants to be like helium. I know that hydrogen can only make a single bond. There can only be 1 bond there. Therefore, the oxygen, if I put in the rest of its dots, it has 1, 2, 3, 4, 5, 6. If oxygen can only make 1 bond with the hydrogen, it can't get its octet, which is why there's not a molecule that exists that's called OH. Okay, but we do have the ion hydroxide. It's very common in nature. How does that happen? Well, the negative charge on the hydroxide represents that this group of atoms has somehow obtained an extra electron. The extra electron, it has to be located on one of the atoms. Well, the hydrogen doesn't need it because by making that 1 bond, he has satisfied his configuration to be like helium, but the oxygen is still 1 electron short. So the extra electron that I have up here, I'm going to put it on the oxygen right here. You'll see sometimes I'll just put a dot. Sometimes people will put an X there. It just represents that's the extra electron. Once that oxygen has the extra electron around it, if I assess the formal charge of each atom, well, I'm kind of looking at each atom to decide, does it have the normal number of electrons around it that it should? I know that oxygen normally should have 6 electrons around it, plus the ones that it's sharing. This oxygen atom, if I look at the ones that it actually owns, it owns 1, 2, 3, 4, 5, 6, and 1 electron in the bond. This oxygen owns 7 electrons. I know that because I gave it an extra one a minute ago, but if I look at it, I have to be able to see with 7 electrons around it, that's more than it would normally have, so the oxygen has a negative charge on it. Hydrogen only has 1 dot that it owns. It's sharing a second one, but that's the normal state for hydrogen, so it's neutral. So overall, this ion, if I add up all the charges inside, we use brackets and we put the overall charge on the outside of -1. Okay, so that is how we write the Lewis dot structure for a ion. Now, let's do one more that's very similar to that one. The ammonium ion. Ammonium is NH4+. So I have my nitrogen in the middle. I have 4 hydrogens around it. Now, if I think about what I'm going to do here, nitrogen normally has 5 dots. If it has 5 dots, that means it wants to make 3 bonds. The most common molecule that involves nitrogen and hydrogen, by no coincidence, is ammonia, which is NH3. Okay? But this is NH4. Somehow we had to change the nitrogen, so instead of only wanting to make 3 bonds, it actually wants to make 4. How do we do that? Well, the positive charge. If the nitrogen loses an electron, it changes from having 5, where it needs 3 bonds, take 1 away, it has 4 dots, which means it's going to need 4 bonds. Okay? So for some reason, the nitrogen has lost an electron, so it only has 4 dots around it instead of 5. Therefore, it needs to make bonds to all 4 hydrogens. But whenever I draw a Lewis dot structure, if any of the atoms don't have their normal allotment of electrons around them, then we have to show the charge. So in this structure, the nitrogen atom is missing an electron, so I put the positive charge on the nitrogen. Again, if there are multiple charges present, then I would want to put the brackets around the outside, put the sum of all charges outside the bracket. So in this case, it's just a +1 charge. The brackets on this one aren't as necessary, but the next one we're going to do, it is necessary. Okay, so that's the ammonium ion. So now our next challenge is going to be the sulfate ion. SO4 2-. So for this one, I'm going to put the sulfur in the middle. with the oxygens around the outside. Now this will be the first case that we've had where we're actually going to go past the octet. How do I know I'm going to go past the octet? Well, sulfur normally has 6 dots around it. It normally only wants to make 2 bonds. Well, in this molecule, if I'm going to connect all the oxygens to the sulfur, I'm obviously going to have to exceed 2 bonds. So this is going to be a case where the central atom will exceed the octet. I know we haven't done that before, but it's okay. It does happen in a lot of molecules. We follow the octet rule when we can, but we have to also recognize there are a large number of molecules out there where the octet rule doesn't work. Okay? Now, what does work is that even if the central atom will exceed, or in some cases be short of the octet, the atoms around the outside will pretty much always get their octets. Okay? So remember that. If something breaks the octet rule, it's usually the central atom. It is rarely going to be on the outside atoms. Okay? So, sulfate has a -2 charge. I have to think about what I'm going to do with the 2 negative charges. Well, essentially what I'm going to do, I know that each oxygen around the outside, if they're going to get their octet, they would normally have 6 dots and have to make 2 bonds. If we do that, that's going to make the sulfur atom make 2, 4, 6, 8 bonds to all the oxygens. That's a lot. If there's anything we can do to reduce that, it'll be to the advantage of the sulfur. So what I'm going to do, the negative charges, I'm going to give those to the oxygen atoms. It doesn't matter which oxygens I give them to, because actually as we go through all this, we're going to realize that all 4 oxygens are actually equivalent to each other. They're all spread out around the sulfur. They're the same. So I just have to pick 2. I'm going to give a negative charge to this oxygen, and I'm going to give a negative charge to this oxygen. Okay? But again, I could have done any of them. They could have been across from each other or on the other side. It doesn't matter. Now, if I give a negative charge to the oxygen, what does that do to it? Well, an oxygen normally has 6 dots and wants to make 2 bonds. If I give it an extra electron, now it's going to have 7 dots. So I'm going to draw those. 1, 2, 3, 4, 5, 6, 7. By giving it that extra electron, now it only has to make 1 bond. So he's going to make 1 bond to the sulfur. This one's going to be the same way. Make 1 bond to the sulfur. But then the 2 other oxygen atoms, they're normal. They're going to have 6 dots with 2 bonds. So I'm going to make a double bond with 2 lone pairs, and then another double bond with 2 lone pairs. Okay? Now in this case, I need to look at sulfur. Sulfur is supposed to have 6 dots around it. 1, 2, 3, 4, 5, 6. It has the electrons it needs, so sulfur is neutral. I do have multiple atoms that are charged, so this is one where I would want you to put the brackets on the outside. If I add up all the charges in the molecule or ion, it should equal the overall charge that goes outside the bracket. In this case, -1, -1. My charge is 2 negative. That is the structure of sulfate. One variation you could have, if several people drew this structure, their single bonded oxygens with a negative charge might not be in the same position as mine, but as long as you have 2 single bonded oxygens and 2 double bonded oxygens, then the structure should be good. Okay? Do 2 more of these. Next one we're going to do is phosphate. Phosphate is PO4 3 minus. I'm going to go a little faster on this one. Phosphorus goes in the middle, 4 oxygens around it. I have a -3 charge, so that tells me that 3 of the oxygens are going to have negatives. Negative, negative, negative. An oxygen with a negative is only going to need 1 bond and have 3 lone pairs. So there is a pattern there that I'm following. The oxygen that doesn't have a negative charge, that's a normal oxygen. He's going to make 2 bonds and have 2 lone pairs. Phosphorus is in group 5, so I would expect phosphorus to have 5 dots around it. If it's making 5 bonds there, again, it exceeds the octet, but it does have the 5 dots it's supposed to have, so that is going to be a valid structure. Again, if I draw my brackets, the total charge of everything on the inside is going to be 3 negative. That's good because it really does need to match. I was given a -3 charge in the beginning. If I drew a structure that didn't have a -3 charge in the end, then obviously I would have done something wrong. Okay. All right, one more. This one's going to have a little trick to it. NO3 minus. The nitrate ion. I go the same process we've been using before. I only have one negative charge, so this time I'm going to give the negative charge to that oxygen. So he's going to have 3 lone pairs, single bond. This is going to be a normal oxygen, so double bond with 2 lone pairs, normal oxygen with double bond with 2 lone pairs. So that's the structure I should be able to come up with pretty quickly. Problem is, it's wrong. Okay, why is it wrong? Well, if I look at my nitrogen, it's in group 5, so just like phosphorus, it has 5 electrons, it can make 5 bonds there, except nitrogen isn't allowed to do that. If I look at the periodic table, nitrogen is in the second row of the periodic table. In the second row, that means that our valence shell is the second shell. In the second shell, the only orbitals that the atom has access to are s orbitals and p orbitals. If I add up all the 2s and 2p orbitals, there are only 4 of them. And if there are 4 orbitals, that means that there can only be 8 electrons. Because if you remember, only 2 electrons can occupy each orbital. What that means is nitrogen can never go over 8 electrons. By making 5 bonds, we've given it 10 electrons. That can't happen. All right, so nitrogen and any element in the second row of the periodic table, they can never exceed the octet rule. You have to remember that. When we get to the third row and below, those elements have s orbitals, p orbitals, and d orbitals. And with d orbitals available, that allows phosphorus and other atoms like it, they can throw some extra electrons in those orbitals when they need to, and then they can exceed the octet. Okay, so that's an important rule that everybody needs to know. Now, looking at this structure, again, this is an incorrect structure. I need to do something to fix it. What I have to do, the nitrogen is not allowed to have 5 bonds, so I actually have to take one of the bonds in a double bond. I'm going to take one of the bonds away. Those 2 electrons, I'm going to take them away from here and move them out and make them a lone pair on oxygen. I have to remove them from the nitrogen atom. So, if I take away one of the double bonds, so this is now a single bond right here. The 2 electrons that were there, I'm going to move them out here as a lone pair. But now when I do that, I've shifted electrons from the nitrogen to the oxygen. That's going to change my charges. So, if I look at nitrogen now, nitrogen's supposed to have 5 dots around it. If I count 1, 2, 3, 4, it's missing an electron. So the nitrogen now has a positive charge. And then this oxygen, where I shifted the electrons out, it now has 6 lone electrons plus the 1 in the bond of 7. It now has a negative charge. So by moving that bond out, it created a positive here and a negative here. If I add up all my charges, negative, negative, positive, the sum of that is -1. Which is what nitrate is supposed to be. So even though I've moved electrons around a little bit, the overall charge does still match what we were given in the beginning. So that's it. Have a good day.